Okay, so I can start because most of the time the beginning it's not something important. My name is Nico Pisanidis. I'm a major from Greece, IT, so this is not very important. I'm working in the CCD COE in the technical branch the last 2 years. So our session is on protection of weapon system. This actually came from a nice paper that we have in our proceedings. I will suggest you to read that. I know that the book is nice to be like a souvenir in your library, but would like also you to read it. So that's what it's for. So the concept, before I start, I would like to remind you the app. Please use it not only just to see the agenda, but please give us feedback on that. There is a survey. There you can rate the speakers, the moderator, the sessions. So we really like to know your opinion about that. Okay, so in the recent network-centric warfare, we have legacy systems and new systems. And these need to communicate themselves, but they somehow pose new threats. So we'd like to know what kind of threats they are there, what are the most dangerous. But also we'll describe how we need also to secure our supply chain, because this is also an issue that mostly in Europe we haven't considered deep. And then we'll go even more technical, and we'll describe about manipulate chips and how we can discover that, if they exist, how we can put backdoors or Trojans in a chip that we import from other countries with low cost. Okay, so first of all, I would like to introduce our panel here. From left to right, we have Dr. Robert Koch. Welcome. That he's a research assistant in the Department of Computer Science in the University of Bundeswehr in Munich. Okay. And also he's a member of the University Research Center for Cyber Defense. Thank you for coming here. We have Professor Mikael Grimaila, that he is head of the Department of System Engineering and Management in the Center of Cyberspace Research of the Air Force Institute of Technology of the United States of America. And last but not least, we have Dr. Georg Beger. Okay, I said it correct. He's a postdoctoral researcher in the Embedded Security Group, Institute of IT Security in the University of Bochum. Welcome, all of you. So, thank you for closing the door. Well, what is the impact of the aids of a weapon system? Can we identify the influencing factors on that? And what kind of countermeasures we can take? So I guess that Robert can give us some presentation, some answers to that. Yes? Thank you, Robert.
Thank you very much, Nico. Thank you very much. Ladies and gentlemen, it's my honor to use the next about 25 minutes to talk a little bit about weapon systems and cybersecurity. And we have a lot of challenging questions and a very challenging situation there at the moment. So if you have a look to the weapon systems on the battlefield nowadays, you have an overwhelmingly complex situation because, for example, every single fighter, every single frigate, there are dozens of networks and thousands of systems in every piece of military equipment, and on the battlefield they have to work together, so a very complex situation. From the design aspects here, normally we are building these systems, high-value military systems, on home soil, maybe together with partner nations and people we trust. But if you have a look into these weapon systems, the inner heart of it, we are using commercial off-the-shelf products nowadays in a very huge amount. And yeah, because of price reasons, of the money we can spend, often we use equipment which we buy from foreign countries, which maybe are not so trustworthy for us, where you don't know, okay, maybe the hardware is manipulated. For example, having a look back to 2012, we had a discussion about the Semi-Pro R63 processor, and it's quite interesting discussion. So some researchers detected a backdoor built into the hardware, and this processor is used, for example, in the Dreamliner from Boeing, in different military jets and in crypto devices, so very common. And that's a problem. Of course, in the discussion afterwards, you often say, from the company perspective, yeah, that's not a backdoor, that's a debugging functionality or something we forget to put again out of the chip in the end. But that doesn't matter, because if you have the stuff inside of your chip, you have a problem. So that's a very interesting discussion back in there. And we will see even more sophisticated manipulations, which are nearly impossible to detect in the real world environment. And Georg will present very interesting research on that topic later, how to build in that and how difficult it is to detect. We also shouldn't forget standards, because for the communication of our weapon systems, of course, they need the same protocols and stuff. So for a network-centric warfare scenario, we are forced to use standards. And of course, also it's possible to manipulate the standards. Think, for example, to the NSA and the manipulation of the elliptical curve. The standard was put into the NIST, one of 4 elliptical curve standards. Or another example, think about the A51 encryption of the GSM networks in the 90s, where the British government put some efforts to weaken the encryption by setting 10 bits to 0, so it was quite easy to break. So if you have such standards and you don't know about some vulnerabilities, of course it's an endangerment of your weapon systems. So having a look at, is that only some fiction, or do we know some cases? For example, Operation Orchard back in 2007 was quite interesting. To that time, the Israeli forces go into Syria and destroyed a nuclear facility. And that was no stealth technology or anything else for the jets involved. So the question was, why didn't the radar systems, and they had some quite sophisticated and modern Russian radar systems beside old systems, but they were not able to detect the jets. So they went in and destroyed the nuclear facility. And in the discussion afterwards, there were 2 mindsets. One said, okay, maybe there was a hardware backdoor or manipulation of a chip, which enabled the Israelis to disable the radar, so no detection was possible. Or the other side, maybe there was some software involved, like the Suitor project that was developed by BAE Systems for the US forces, which can be used to do some quite sophisticated change of the information which are in the radar system. So I will come back to that a little bit later. In the US, they started already back in 2003 the development of a trusted foundry program, because they identified, okay, we have a lot of vulnerabilities with these IT parts coming from not so trustworthy countries. So they basically they said to IBM, okay, don't close this chip fab. We will pay you that you continue the production for chips, especially for high security areas. So IBM was giving the factory, and they selected about, to that time, 52 suppliers which are trusted and which are doing all the supplements to the production process. Nowadays, that's over 70. That's not enough to put everything in your systems with trustworthy hardware, of course, but for the main aspects, for crypto devices and stuff like that, they are able to generate these processors on home soil in a very trusted environment again. Anyway, a study in 2011 showed that about 40% of all systems in US government and the military were affected by counterfeit electronics. And if you have counterfeit parts in your system, the chances increases that there is some manipulated hardware within. So looking back again to the battlefield, we have a huge range of high-value and elderly systems. Of course, if you pay several billions for a system, you can't say the taxpayer after 3 years, oh, it's outdated, I need a new one. So these systems are operated for decades, 40, 50 years, that's not uncommon. So we have to think about, okay, maybe the elderly systems are not so sophisticated, there's less IT technology in it, maybe we have to differentiate that. We will see that in a moment. The big problem for the very new system, the high-value systems, as I said, you have to operate them for about 40 or 50 years because of the high costs related with that. On the other side, the commercial off-the-shelf equipment, which is built into that devices, the life cycle is much shorter. So we have the system, we have to operate for about 40 or 50 years. But the hardware inside, the lifetime, for example, that's for a surface system printed over there, in 24/7 working, you have a time about roughly 2 years. Of course, the system don't have collapse only because you reach the mean time between failure, but of course, the chances is increasing. And if you have a look at the operational environment, for example, a frigate going through heavy sea with 6 meters of waves, and in some oceans where the temperature is very high, these systems are really stressed. So sometimes it's quite wondering how good they are working, even under these conditions. Anyway, you have a big problem because you have to exchange that hardware regularly to keep your systems running. Looking again to network-centric warfare, the basic idea, of course, is being more efficient with less resources. So connecting all the sensor information, giving a fast decision opportunity to the commanders on all levels, and then applying the effectors in a very fast and precise direction. So getting more benefit, being more efficient with less resources. Of course, all the systems have to be interconnected. And that's the part of the weakest link in the chain. So the already very complex situation of the single weapon system is exploding here in the network-centric warfare scenario. Back to the old and the new systems. Because of the numerous times you have to exchange the hardware which is built into the systems, you can say, okay, you have to treat the systems equally. Because sometimes only the hull is quite old, maybe about 30 or 40 years old, but inside of the system you have brand new hardware equipment working to keep the system running. So if you have a look at the battlefield, you just have to treat every system equally. A huge challenge is the defense technology and industrial base. So that's all the manpower, the knowledge, the production capacity of a country, which is required to achieve national security assets. In Europe, in 2007, the European Commission wrote a strategy, a DTIP strategy, to better coordinate our projects and reduce the number of duplications. So trying to have a better usage of resources. And a few years later, in 2013, overview was given, what has been reached over these years. And bad news, like often with those projects. So in 2013, they said, okay, a European DTIP is increasingly improbable. So we are standing quite still. The situation is even getting worse. We are not able to collect our energy to single projects and putting more out of that. Coming back to that also. The supply chain of the processors. We said, okay, we have a lot of equipment and we have to buy that in different countries because of the price. So the picture gives an idea how complex the situation is nowadays. A processor, maybe the design is made in one country and the production process is shared between different countries. And for example, even for building one processor, it can be that the manufacturer is buying a complete part of the design from another manufacturer, for example, floating point arithmetics, and not building that by itself, putting it into the processor and then building the new one. So very, very high complexity of the chip design ecosystems nowadays with a lot of involved countries, peoples, and companies. And in every aspects of these design steps, manufacturing and testing, you have opportunities to influence the process, to put backdoors in or do some other stuff. And only to have an idea, that's the F-35 from the US. You also can have a look at the Eurofighter or other projects that are weapon systems where a lot of countries are related to the production process. Here are some ideas where in which countries and which companies are producing parts that at the end fit together to the plane. And yeah, a lot of weak links you can build by that. So quite interesting having a look back to the case. Some interviews were made in 2008, and one said, of course, there is no name, that one European chip maker is already building some hardware backdoors or some kill switches. So kill switch, you can disable the circuit. Building some kill switches into the product. So in case that we lose the weapon system, for example, the jet is going down somewhere in a hostile country, we are able to disable it from remote. Every nation, of course, may have these interests, and if some nations are producing the inner heart of all your weapon systems, maybe you are in a bad situation. So that's a quite nice background here. Another threat, compatibility. Of course, we need that. SCSI is a very good example. SCSI is a very good protocol because it's very compatible. Expect to other areas. So you can, for example, take a quite new SCSI 320 hard disk and put it to a quite old SCSI 2 controller. And if you take the right cables and stuff, then that's working. In theory, at least. In practice, you have some more challenges because sometimes the signal leveling is a little bit different, and then that's not working the way you expect it. And that's a problem. If you think, okay, I will put this system into my weapon system and no problems with compatibility over the next years, and then you are buying the stuff and put it in and it's not working again, you have to think about that. Also, the shelf life is a quite challenging problem. As you can't put parts for about years in the shelf and put it out, putting it into the system and then expecting, okay, it will work again, because there are chemical processes and other stuff. So if you're not using it, if there is no power on it, the chance is quite high that after 10 years or something like that, the parts you have in the shelf are not working any longer. So having a look at some countermeasures, we identified 5 areas, and of course some are quite expensive, for example, building new production capabilities. Others are more paperwork, let's say it this way, and have a look to the different ones. Because of the situation with the commercial off-the-shelf products, we can't change that. It's not possible that we are building capacities from tomorrow or until the day after tomorrow and exchange all the endangered parts in our high-value systems to make it more secure. So we have to live with the situation and have to cope with it. And a basic aspect to do that is emergency planning and risk management. So you have to look at your weapon systems, and for every system, for all units, but also on all management levels, you need reactions and countermeasures for worst case situations, emergency and disaster plans. And because the situation is so complex, of course you have to identify the vital components. If you're on the battlefield, what is a worst case situation, which component can fail, for example, communications, encrypted devices, and how to react. So you need appropriate plans to deal with that. And frameworks like COVID-5 or the NIST special publications, they can be used to build up such emergency planning and risk management. For the supply chain and DTIP, of course, the situation is quite complex, so you have to try to improve the security of the supply chain. There's a lot of research going on in that area, but often academia and real world has some huge gap in between. So nice ideas, but very hard to put them into practice. So we need more projects that can be applied for the real world to make the supply chain more secure. And of course, programs like Horizon 2020 can be an opportunity to give funding to such research. The strengthening of the European DTIP is another aim. Also, the European Commission, for example, is trying to do an effort. Even a European chip fab is in the discussions. But we have a long way to go there, and at the moment the situation is that the defense industry mainly is doing national business and focusing on export because they can't survive only based on the military projects of their own country. So we are not on the way to have a strategic vision of a European DTIP where we can improve that situation. Hardware regeneration by design is a very important aspect. As I said, you have a very long time where you have to use your high-value weapon systems, 40, 50 years or even longer, and you have to exchange the IT core at least every 10 years, every 15 years. The hardware is running much longer than the normal mean time between failure, of course, but you have to do that quite some time. And you need better programs for that. If you have a look again to the US, they started this when they built the aircraft carrier Ronald Reagan. So they had in mind, okay, from beginning of the design until we put the ship into service, the system is completely outdated, and that's for every high-value system. Have a look at the Eurofighter when we started the development in the 80s, and when the first plane arrived. That's for every complex defense project, that's the same. So they started the vision, okay, we have to exchange and upgrade the systems and build the ship in a way to ease that a little bit. And the upcoming ships after that, they are going further and further to do that. In some of our procurement projects, we are not so far. So we have to pick up this mindset and try to build the systems that we can upgrade and update the inner parts and the IT parts of the systems more easily. Also, we need concepts what to do when some compatibility issues arrive. So yesterday the system was good on paper and compatible, and we have products the next 20 years, but one day later the company is not there, or a new standard arrived which is more successful, and that can be very fast in the IT world out there. So we need concepts, what to do, what to exchange, how to react with the IT systems of our military systems in such cases. Methods for detection of counterfeit or manipulated chips. We will hear a little bit more about that also later. We need more real-world useful technologies for that, because you can destroy a chip and look into it and try to find backdoors and everything. But the technique must be applicable for a huge number of real-world systems without destroying them. And there, a lot of research is still open. And of course, migration strategies, for example, if you have to shift a whole network, a whole IT structure, which is only a part of a whole weapon system, to a new standard, to a new version, also therefore we need some migration strategies. Having a look how the capabilities of the Trusted Foundry program from the United States are used, you see, okay, something is going to Air Force, Army, and the Navy, and NSA, of course, is using them. You see, okay, they have provided a basic setup of secure chips, but of course, it's not enough. Anyway, it's quite interesting example, and you see you can do that if you are willing to take some money. Good news, we are not completely lost and not everything is sold out, what is IT and chip fabs in Europe. So for example, Global Foundries invested about $5 billion in Dresden since 2007, and that's the most modern chip fab in Europe. And for example, last year, they put another several hundred millions into the chip fab to go down to the 22 nanometer silicon on insulator fabrication process. So that's really state of the art and a very good product. Anyway, that doesn't fit to any European strategy and something like that. So when the European Commission is talking about, okay, we should build a European chip fab, then that's not in mind with this fabric and how to deal with that and how to get the best benefit for Europe and the high security systems out of that. An example would be, and you can see if you look in the proceedings to the paper, a little bit more information about that. And maybe you should also read the source. It's published by Brigadier General Adams. And he took a lot of cases from the US military and shows all the dependencies from the systems. For example, from raw materials, where they depend on single other countries in the world, up to IT and electronics. And one part, for example, are radio sets, where the risk that untrustworthy components are inside because of the supply chain is very, very high. If we take a look at the countermeasures, at the 5 areas we propose, how can that be in practice? So if you have a look at the systems, for example, in the case that a system drops down, there's a kill switch activated or something like that, you need guidelines how to work with that outage or corruption. You must enable the operator and not only the technician, but the operator, how to deal with that case if it happens in real time on the battlefield. For example, switching between equipment or maybe using that instead of that, or you have to find ways to deal with that. And of course, that is bad to only write papers about that. You have to exercise that in practice, and you have to exercise that on your real world systems. Even the best simulator can't give a real world picture where all of the challenges are inside. So you must take your weapon systems and then saying, okay, from that to that time we are putting, for example, that system out, and now we are looking how our concepts are working, how the operators are dealing with that issue. And especially when we have a look to the communication part, this shouldn't be in the night time between 2 and 3 when no exercise is running, so nobody has a problem with when the communication is down, but it must be in the real world example. If you are doing an operation and in the worst situation when you have a lot of communications and other stuff, then you have to do these exercises and try how to do and deal with that. Appropriate risk management. Michael will tell some more about risk management. So I only focus on one aspect. Because of the complex situation, you must deal with it. So having a look at the battlefield and your operation, you have, for example, to think about, okay, if there is a manipulated circuit within my weapon system, can I use it? What are the conditions for that? So, for example, if you have a ship and there is no connection and nobody is able to access or use the backdoor or the kill switch, then it's okay for me. But you must be able to have a broad view on the possible operation environment and if it's acceptable to take such a risk. Of course, building the fabrication capacities, I told something about that. If you have that opportunity, trying to move first to the high security system, communication system, crypto systems, and then also successively replacing security relevant chips in also older systems. So having a holistic risk management is the basic idea behind that. You can see which parts of our countermeasures are addressing which area. And the problem is really from the beginning of the specification of a part until the disposal. In every step, you are able to do some sophisticated manipulation to get some information out of it. And that must be addressed on all levels with a holistic risk management. So summarized, having a look at the battlefield nowadays, you're confronted with a very, very complex situation of the weapon systems, talking to each other by using different standards and exchanging a lot of information, basically with an IT core that is not trustworthy at the moment. The systems are increasingly vulnerable because more and more of the production capabilities are moving to cheaper areas and around the world. And remember the complex picture about the distribution process and everything. And also very challenging, the diverging life cycle, 40, 50 years of the main weapon system in contrast to a few years of the inner IT core. So what we propose is an organization-wide emergency and risk management for every unit up to all management levels. Strengthening of the European DTIP capabilities. Yeah, the Commission is trying to do that, and the situation is very complex because of political reasons. But that's necessary to make an improvement in the near future for that area. And of course, improving the security of the supply chain, for example, by research activities during Horizon 2020 or something else. And last but not least, concepts for the hardware generation, thinking about, okay, we have to exchange the hardware regularly in the systems, and we have to take that into mind even in the design process of the system, and not too late. Okay, so are there any questions?
Just on time. Just on time. You're perfect. So we'll have time for some questions. Yes? No questions? Okay, 1, 2, 3. Well, actually, thank you, Robert, for that. It was an excellent. It's the first time I don't have a question for that, but you can take your click and grow. Thank you. Well, Robert put the stage right on the level, and I think you didn't really need me to be there, because actually your presentation and your case study is coming just so Mikael, you can talk about what is happening on the other side of the Atlantic. Yeah, we are hoping that you have more experience than Europe and you are more concrete, and let's hope. Yeah, let's see. Okay, thank you.
I think you're giving me too much credit. So my name is Mike Gramila. I'm a professor of systems engineering at the Air Force Institute of Technology. It's located on Wright-Patterson Air Force Base, which is very convenient. There's a number of different weapon systems programs located there: F-16, F-22, F-35, Reaper, MQ-9, and whatnot. So I'm going to talk a little bit about a systems engineering approach for securing weapon systems. The obligatory disclaimer: these are my opinions, not those of my employers. As I go through the presentation, I'm going to first kind of talk about what is the problem, but I think we've already had a good characterization of the problems that you encounter when you're developing any system, not specifically even weapon systems, in terms of securing it. So I'll talk a bit about lessons we've learned, or perhaps haven't we learned. I'm going to talk a little bit about what systems engineering is and why it can provide value. And then I'm going to talk about the new National Institute of Standards and Technology Standard 800-160. It's in the second draft right now, and it's going to be the mechanism that I'm going to share with you, kind of the idea of how we might move forward in dealing with life cycle issues related to securing weapon systems. As was pointed out, systems now, oftentimes are fielded. If we look at the B-52, for example, its expected life cycle was 10 years. It was supposed to be replaced by a next generation bomber thereafter, and here we are in 2016. So you can imagine the difficulties that we face when you try to keep a system going that long. Even if you had, that in mind, the technology has changed quite a bit. So you can imagine there's been a lot of systems re-engineering of the subsystems that are in B52. So naturally, headlines are what people are attracted to. So to motivate this talk, I pulled a headline from Reuters in January of 2015, and it basically said nearly every U.S. arms program has been found vulnerable to cyber attacks. So that grabs the attention. Of course, the question is, what is the source material for this? And if you look at the source material for the article, within the Department of Defense in the United States, we have a position called the Director of Operational Test and Evaluation. And that person currently is J. Michael Gilmore. And that office is the one that's tasked with sampling the systems, weapon systems in the DoD, and conducting testing and evaluation of those systems, also to include cyber testing. And so I'm going to talk a little bit about some of the findings from the original report that article was based on, which was the 2014 report, which was published in January of 2015. But I would be remiss if I didn't also include the 2015 report, which was also released January of this year. So the key findings of this report are that nearly every system tested was vulnerable to some type of attack. Now, I don't think that's probably unexpected in some cases, because there is no perfect security, right? I mean, if you don't believe me, how many units secure is your system? The reality is we don't have a calibrated, scale that we can measure objectively. So what we do instead is we try to collect sets of known vulnerabilities, and we have checklists, and we have STIGs. We have other things that we go by. We have best practices, right? So we try to go off and say, if we do protect the system to some level, that we're happy with that. Another key finding of the report was that a determined cyber adversary could impede the weapon system's capability and/or the mission, and that's a critical concern, especially when we see cases where integrated air defense systems are brought down, perhaps by a cyber attack of some sort. Cyber is interesting because it requires intel preparation of the battle space. I'm not sure you'd want to be the pilot flying over that IAD system unless you were sure that cyber capability designed to take out the IADs was going to work. Another key finding of the 14 version of the report was that a lot of the issues that were found could have been addressed during system design and development. And so this is kind of providing the genesis of the point of the discussion today. Programs need to explicitly address protection needs and requirements during the development of the system, not afterwards. You can't bolt on security and expect it to be sufficient. And so really, if you wanted to nutshell my whole discussion today, it's going to be talking about a NIST standard that drives you towards driving the requirements of the system to include the protection needs of the system throughout the life cycle of the system, from inception, concept development, through design, modeling, simulation testing, verification, validation, operations, looking even forward to sustainment and/or retirement of the system. And so we'll talk a bit about that. So another key finding of this report was that it would be helpful if we actually tested in realistic environments, because too often times we'll get the folks who are involved with developing the system to be the ones who define the operational scenarios in which the system is tested. And so what we see, this is why we have red teaming, right? This is why it's very popular to red team a system, because you're coming at it with a different group of individuals who aren't the people who design the security measures. And you're trying to identify weaknesses that perhaps the designers of the system failed to see. Interestingly enough, if you look at the 2015 report that was published in January this year, pretty much everything that was said in the 14 report was repeated. There were some additional things. There were some common vulnerabilities found. So exposed or poorly managed credentials, systems not configured to standards, systems not patched, because as we were talking about earlier, we have a lot of commercial off-the-shelf technology embedded in these weapon systems. Why? Well, it's because cost. I mean, we can't be developing our own custom operating system, our own custom computers, except for in very, very narrow limited situations. We've become very accustomed to, or addicted to, if you will, commercial off-the-shelf technology. with all its vulnerabilities, and its strengths and weaknesses. But that provides an adversary the capability to mimic your system if they can get a hold of the software, and they could have exactly the same hardware. Another aspect was trust relationships, which were exploited. Too many times during systems development, we'll make it easier to get the system up and running, and we may forget to go back and secure it properly. I mean, I'm reminded of, like when you bring your cable modem and you bring it home and you start it up, you turn off encryption first to make sure that you can connect to it, and then you turn on encryption and you get it secured and whatnot. A lot of people skip that step who aren't knowledgeable about security. You'd be surprised at developers who have systems that say contain a database. And in the interest of making it simple, they put no password on the database, or they hard code the password somewhere where it's easy to find in the access of the code. So another finding in the 15 report was, hey, we got to do a better job of doing realistic testing so that we can identify vulnerabilities in the testing process and not later when it will hurt us. If we look at the Scientific Advisory Board, which is the United States Air Force puts together each year a scientific advisory board, and they pick 2 or 3 different challenge problems, and they bring in people from industry as well as the defense sector, military leaders, to study some problems, okay? This particular one addresses vulnerabilities in avionics systems. And so once again, I just highlighted one of the many findings. You can go and read the summary that's out there. But basically, a lot of it has to do with making sure that you have processes and tools in place to verify and validate that things are operating appropriately and that you can identify weaknesses sooner rather than later. So what were the lessons learned from these reports? Okay, classically, a weapon system is truly a system of systems. I mean, if we take the semiconductor circuit, I'm a double E, bachelor and master's, and I got a PhD in computer engineering. So I studied the development of chips, fabricating chips. I fabricated chips, tested them. But to me, that was my world. That was my system. But when you put those chips together into a circuit board and do a larger subsystem, a module, if you will, that could be also considered a system. Then if I put that module together with other modules to create a bigger system, that could be the universe of what you call a system. So it's a recursive relationship that occurs here. The techniques that I'll talk about in systems engineering and subsequently system security engineering could be addressed at many levels. But your concerns will be different. If I'm just manufacturing a chip, I may worry about static protection. I may worry about blowing fuses to make sure the backdoor, testing stuff is not available to an adversary. But that would be kind of the universe of things I'm interested in. As you grow in the scope, the complexity of the system, the interdependency has become more difficult to reason about and to be tractable. And it also becomes more difficult to retain knowledge related to how you put together the system so that when it comes time to refresh the technology, that you have good documentation about what was there. So some of the emergent properties that we see within a system are reliability, safety, security. These are things you really can't reason about until you put the whole system together. And when I say system, I want to point out I'm not talking just about hardware or software. There's people, there's processes, there's environments, there's contexts. You really have to look holistically at security, as you said, to really understand or to reason about the security. Some properties are not formally, cannot be formally reasoned about. For example, I can't say the system is provably secure unless it's very, very simple, and then I can mathematically represent provably secure. When you're talking about the systems that we're talking about that involve many different subsystems, many different communication networks, many different links, many different contexts of use in the battlefield, it's very difficult, if not impossible, to do a formal security proof. So we have to be doing holistic security. We have to think about security from cradle to grave. We have to do the right things right, and I'll talk a bit about what that is. And we really are looking at towards a system or a mission risk management concept in the systems engineering process of designing the system. So let me first talk about the importance of systems engineering. The Department of Defense recognized early on that we were often acquiring systems that were built by contractors that had specific purposes, and that when we tried to upgrade or retrofit those systems or replace subsystems, it was very difficult, if not impossible, to develop interoperability. So as a consequence, there's something called the Department of Defense Architectural Framework. You've probably heard of DODAF. DODAF is a set of views, or it's a collection of products that are used during the application of this thing called systems engineering, okay? And systems engineering, more broadly defined, is a set of technical and non-technical processes with the objective of getting you to your objective system that you're trying to design. But the DODAF architecture is very interesting. Some people hate it and don't use it properly. Some people call it the $900,000 book, doorstop, because you go through all this documentation and it doesn't provide a lot of value. Other people embrace it and understand that the architecture represents the system. And ultimately, if you want to reason about the functionality of a system, one must have a great understanding and in-depth representation. So if you look at DODAF products, now when you look at them in abstractness without looking at them applied to a system, they may appear very dry. You have things like behavioral diagrams, you have system interface diagrams, you have a collection of products that each one provides a different view of the system from a different angle. And I'm pointing this out because the next standard that I'm going to talk about is based upon the concepts of systems engineering. So systems engineering has proven very successful in the development of large, complex systems. It provides the ability for you to elicit requirements from stakeholders, document them, look at transformations from those requirements into a system design, define performance requirements. It allows you to go through the whole design process. And if I had more time, I'd tell you about it, but I'm not going to spend all my time here because I'll run out of time. But the important thing is, from cradle to grave, you have a set of processes that are defined that help you walk through the engineering process and provide a traceable means to tie a requirement to an outcome. And that goes through every step of the design phase, which is really important, as you'll see shortly. So what I'm going to talk about now, given the fact that I've given you a very brief summary of what systems engineering is the NIST standard 800-160, which is in its second draft. It represents a 5-year culmination of an effort between the National Institute of Standards and Technology, the National Security Agency, private sector security organizations, and academia. It is not a prescriptive standard in the sense it's more a collection of activities that one would do if you wanted to properly secure a system through its life cycle. So it's a 302-page document. The first maybe 30 pages give you a good background. The rest are appendices. And when you look at this standard, you really have to look at ISO standard 15288, which is entitled Systems and Software Engineering. And that standard, that ISO standard, identifies a lot of the systems engineering processes. There's actually 30 of them that when you're doing engineering of a system that you should follow. So this kind of piggybacks on that and tries to provide detail about the security aspects of each of those 30 processes. So actually, if you look in the appendix of this document, you'll see that they're tied to each of the 30 ISO standard processes for system and software engineering. So when we think about what is systems security engineering, it's a sub-discipline of systems engineering. So it's not something you do separately. Once again, I want to point out that the idea here is that you want to run concurrently your security systems engineering as well as your systems engineering during the design process. And this can be applied in many different phases, but within the system security engineering, you have different sub-disciplines. I might have cryptographic technologies subspecialty. I might have a communication specialty. I might have a anti-tamper. So each of those bottom bubbles represents a different specialization area that it's all brought under the umbrella of system security engineering that must be considered when you're putting together a system. The main idea of this standard is that you want to upfront drive or elicit the protection needs as enumerated by the stakeholders that are involved, the system implementation stuff that is involved, and from the different traits. When you're looking at systems engineering, it's an amorphous thing because consider the design of an aircraft. So when you're designing an aircraft, you have weight, you have thrust, you have, navigation issues, and they're all interrelated. If I increase the weight of something, I might have to increase the thrust. It's all a set of competing objectives. So the purpose of the standard is to help you think about up front, what are the protection needs of the system, broadly defined. When you have those, you can transform them into formal security requirements and security policies. And once again, when you document this stuff, it's enduring. And you may not get it right the first time, but you have kind of a template that you follow, if you will, that allows you to build out this understanding of the system in terms of security. Now remember, separate from this, going with this in parallel is the systems engineering process proper, which is more focused on, does the system perform its intended purpose? So this aspect of it is more dealing about the protection needs. So you have to explicitly enumerate them, and once again, you trace them from beginning concept, design, development, test, validation, verification, and whatnot. So if you look at systems engineering framework, system security engineering, it's basically a high-level conceptual view of the system within the different activities that we talked about. It ties together those technical and non-technical activities, but the critical thing is it provides an evidence-based assessment of whether or not your protection needs have been met. Now this sounds easy, but it may not be so easy. It's difficult sometimes to enumerate the requirements, but we're moving in the right direction by requiring that you explicitly define what it is that you're trying to achieve. Because if you don't know where you want to go, how are you going to know if you get there? And so it's a challenge to do that. It's independent of the type of systems engineering process. Some people are doing rapid spiral development, other people are doing the traditional waterfall method. This concept of system security engineering is an iterative process. Its purpose is to provide that traceability from system requirements to the implemented system. So systems engineering and system security engineering is all about developing a documented understanding of the system and what its requirements are, so that you can develop the tests and verification and validation methods. You can conduct the trade-offs between design trade-offs and implementation. You can document when you have to replace a subsystem, how I might replace it with another subsystem and still have the assurance that the system works as intended. In the standard that they talk about 3 different contexts. They talk about the design context, the implementation, and then the trustworthiness of the system. And they use some terminology like the idea that it addresses security from a stakeholder's perspective. Because in the end, you're not going to have a perfectly secure system. You're only going to be able to design in security commensurate with the value of what you're protecting. As we all know, we live in a world of constrained resources, so this allows you to document, if you will, what the requirements are, so you place the resources where they need to be, and also that you formally document what it is that you're trying to protect against. So if there was one slide that kind of captured this concept, it would be the ISO 15288 standard systems engineering lifecycle processes. Now what they've done, if you look under those different activities, there's 30 of them, 30 processes enumerated there. For each one in the ISO standard, they have in this NIST guidance flushed out the details of what one should do. Now the NIST document is not intended to be a prescriptive approach. It's more like a guidebook, something that you could adopt some or all of the recommendations, just like DODAF is a set of guides. When I'm teaching systems architecture, we have to go through every product in DODAF and say, here's what this product is, here's what it does. But when you actually design a system, you may not generate every product. You only generate the ones that provide value in understanding the system. So similarly, you may choose not to implement all of the processes, but at least you thought about it, and you thought about the implementation issues. And as I pointed out, it's an iterative process where you have feedback loops going on. So no doubt weapons system security is critically important. This new standard by NIST, which is in its second draft, first draft was 2014. The second one was released in May. I think they're gonna finalize it in the end of the year. Provide some guidance on how to formally address protection needs from the stakeholders' views to achieve a system that meets not only the functional requirements, but also perhaps is more secure. And they talk about the concept of adequate security. Adequate security being protecting against those risks commensurate with the values of the assets they're protecting. And there are no silver bullet solutions. But this provides a pretty good framework on how to get there. So in closing, the value that NIST 800 and 160 provides is to formalize the discipline of system security engineering. There's a lot of good references that are available in the document. So it's not intended to be, here's the answer. It's intended to be, here are questions that you could frame together to help you get to the answers, because every system is different, every requirement's different. It helps you develop the mindset that you need to bake in security, not bolt it on at the end. It also provides evidence-based verification and validation so that you have some way to prove when you've developed a system whether or not it meets the protection needs. And that creates that feedback loop that we were talking about, where you basically have to sometimes go back and revisit the requirements or adjust the requirements or redesign a subsystem to meet the needs. So in closing, that is kind of the summary of NIST 160, and I'll point out the references here, which are available in the slide deck, and you could download it from the draft. But other than that, I think I'm done.
Thank you, Mika. Thank you. I don't know if we have any questions. Well, my impression is that on the other side of Atlantic, at least you're aware of that and you're doing some steps. This NIST is something valuable also for Europe. But have you seen, I don't know if the panel has any question. Robert, no? Okay. So have you seen any improvement from your report of 2014 to 2015, and how NIST also, these guidelines helped you to do that?
I'd say absolutely yes. Not necessarily driven only by the standard, but the whole concept of driving protection needs up front in the design process has paid big dividends. It used to be that the only thing that a project manager would be concerned about are budget, schedule, and performance, and they would have an annex that they'd at the appendix of the program that would deal with critical technologies and the protection of those critical technologies. But they really didn't have formalized the requirements for protecting the system in operational use. It was more about, what if this gets shot down? How do I protect that custom chip, for example? So what we've seen is more and more folks using it. I want to point out that NIST 800-160 is not directive to systems that are involved with national security. However, program managers can adopt the philosophies, and they do adopt the philosophies in that. So we've definitely seen an improvement. Basically, it's been an evolution of thought. People recognize that we have to do something, and it's better to start early rather than try to bolt it on afterwards.
Yeah, I guess that everybody needs to understand that security by design is less costly afterwards, yes?
Yeah, cost
whatever cost means.
Yeah, it used to be that cost was, hey, if I just want to get the system up and running, I'm going to minimize my costs. I don't care so much about that other stuff. But we're recognizing the overall cost, the burden cost, is important to bring into account, especially if you hold a program manager accountable for developing an insecure system.
Okay. Thank you, Mikael. Okay, you have your click and grow.
Very good.
I hope you can take in states.
Yeah,
Congratulations again.
Thank you.
Thank you for having you here.
You bet.
But most of important, all these are just words. So we'll try to make some more deep technical issues. I hope you will not escape. George promised that he will not be too technical. I know that most of you are tired. But is it technically possible to insert Trojans in a chip? How we can identify if a chip is manipulated or is a counterfeit? So the floor is yours.
Thank you. Yeah, so this will be the most technical talk, but as Nikos mentioned, I'm trying to make it brief with the technical part, and also keep the non-engineers here interested in the talk. And the topic is hardware Trojans and whether it's a realistic threat. And the agenda is as follows. I'm going to first introduce what are hardware Trojans, at least what are hardware Trojans when we talk about it in the academia, and how can they be inserted. And then also, can they be detected? And if they can be detected, how can they be detected? And then comes the technical part. I want to give you an example of how a hardware Trojan could look like for you to get a feeling what hardware Trojans could mean in practice and why they are so dangerous and hard to detect. And then finally, I'm going to give some conclusion and personal opinion, trying to answer the question of how realistic these hardware Trojans really are. So first, the question is, what is a hardware Trojan? So the definition that is most common says it's a malicious change or addition to an IC that adds or removes functionality or reduces reliability. There are two words here that are important. The first one is IC. So IC means integrated circuit. So we're talking about a chip. We're talking not about the whole system. We're just talking about a single chip, a single computer chip. And the second part is malicious. So if you look at computer chips, they often have bugs. They often are insecure because, like every other digital system, there are mistakes. So you can probably attack them. But in most cases, it's unintentional, right? They wanted to build a secure system, but they just failed. So we are talking about hardware Trojans then when it was maliciously changed so that it would be insecure or that it would have this functionality that it's not supposed to have. Because not everybody of you is probably familiar with the design process of a chip, this is like a very brief overview how a chip is designed. We start off with a specification that defines, okay, what should the chip do? And then we have the design phase, which, as mentioned, is very complex. So designing a chip nowadays is quite difficult. So you don't design it from scratch, but you buy parts of the designs from other companies. Finally, you have your design, and in many cases, nearly most of the semiconductor companies don't have a fab, so they cannot fabricate it themselves. So they send the final design to a factory. They actually manufacture it. Then the chip needs to be tested and packaged. And then, in most cases, they are sold to distributors who then sell the chip to you if you're a company. So the question is, where can a Trojan be inserted into this complex design phase? And the answer is pretty simple, everywhere. So one of the most prominent examples is the manufacturing stage. So that is, can you trust the factory where you produce your chip? This is often motivated with, by the case that it's often located in a foreign country where you might or might not trust the government. Also, the design phase, of course, can be an attack point. Like I mentioned, many of the designs, parts of the design are bought from other companies. So if you buy an IP core that, for example, is an encryption core, it's supposed to do an encryption, how do you know that it only does what it says and doesn't leak out the key if you send some magic number to the core? Or malicious employees, like could be a cause of a Trojan. And also normal, let's say normal software Trojans can be used to insert a Trojan. Imagine, for example, you hack into a server of a company and you replace one of these IP cores that are legitimate, that are great, with your malicious IP core. Right? So that could be also another threat, how a hardware Trojan is inserted. And finally, chipping assembly. I think we heard a lot already about the counterfeit problem. So what happens if you simply replace the chip with a different chip that has this malicious functionality? And last not least, we have government requests. So what happens if already in the specification there was some malicious intent and the chip has a backdoor that you are not aware of, which is, of course, also a big problem. Actually, from a classic perspective, when we're talking about hardware Trojans, most of the time we're talking about this manufacturing stage hardware Trojan. And then the question is like, how recent is this trend about research in hardware security? From an academic perspective, it's actually a rather young topic compared to other topics. It really started off, I would say, in 2008. There were like an important paper by King who showed like how dangerous a hardware Trojan can be. And since then, it's rapidly increasing. So now the research community really has picked up, but it's fairly young topic still. And in 2005, there was a report from the Defense Science Board of the US, which mentioned this manufacturing level hardware Trojan problem. And that also is one of the reasons this whole research got started, because a lot of money was spent also, for example, by DARPA and in the US in general on this hardware Trojan threat. So the question is, where are we with real hardware Trojans? No hardware Trojan observed in the wild. When I say observed in the wild, I mean known to the public, to academia. So we have heard like rumors, so there might have been hardware Trojans already, but we don't know any details. So all concrete examples of a hardware Trojan are from academia. And also, most of them are actually quite high level. HDL means the design stage. But the vast majority of publications actually focus on detection, trying to detect these Trojans, and mainly focus on this manufacturing stage Trojan detection. So I said there are no real hardware Trojans yet. There's a small however. We already heard a lot, so I'm going to be brief about that counterfeit chips ended up in military systems. And in many cases, counterfeit means that you have, for example, memory that is grade B or grade C that is sold as military grade A, which basically means they have the same functionality, but it's not as reliable. So you have actually removed the reliability. I think in most cases to make profit, not with this malicious intent of reducing the reliability of your system, but it's getting close to a hardware Trojan. And also, I mentioned hardware Trojan when we talk in academia, we're talking about a chip, if a chip doesn't do what it's supposed to do. If we broaden it, for example, a USB cable, we know from the NSA documents released by Snowden that the NSA interdicts, for example, shipments of keyboards or other things that have USB cables and put an RF transmitter into the USB cable so that they can overcome the air gap in closed systems. So in that sense, it's not a hardware Trojan because they add additional chips to that device, but again, it's getting close. They might also do it with manipulating chips. So the question is, how do we detect hardware Trojan? So how do we detect that the chip doesn't do what it's supposed to do? The best way to do it, or like the securest way, would be formal verification. What is formal verification? It basically guarantees that your design does exactly what the specification says. Okay, so you can guarantee that your chip does only do what the specification says and nothing more and nothing less. The problem with this approach is it's very expensive and it can only be done with small systems. If you have like a modern processor, it's pretty impossible to make formal verification of the entire processor. And the second thing is you can do it with design, so Trojans that are inserted into the design. So if you get a third-party IP core, you might be able to do this formal verification, like when it's a small part. It's more costly than developing it, actually. So you might just do it on your own. And again, if the Trojan is inserted to the manufacturing, it doesn't help. The next step might be functional testing, which is done anyways. So you have to test if your chip is doing what it's supposed to do. You can do it at all stages, and you should do it at all stages anyways. But the problem is that a hardware Trojan designer can design it in a way that it doesn't get detected using this functional testing. And we're going to see an example of that later. Another thing is optical inspection. So you basically remove, you make a picture of each layer of the chip to see if somebody added something to the chip, to the design. And that is aimed at the manufacturing stage. So you can make sure that no additional transistors has been added by the factory to enable this Trojan malicious activity. And then we have side channels, which basically means, it was also mentioned, the optical inspection is destructive. So you open the chip, make a picture at the end, you know, yeah, this chip that I just destroyed has no Trojan inside. But what about the next chip? So what you do is you can measure side channels such as the power consumption and compare the power consumption with what you expect. And if the power consumption changes drastically, then you can expect that somebody modified the chip somehow. The problem with that is that you usually need a golden model to compare to. And there's also research to have dedicated Trojan detection circuitry. My personal opinion is not too high on that part because the problem is how do you verify that the attacker doesn't modify that circuitry as well? Because he can modify other parts. And most papers are actually about the side channel part detection, and I think the other part is a little bit under-researched. Now we come to actually the technical part. So I want to give you a case study of how a very stealthy hardware Trojan could be built, which is actually was kind of the final product of my PhD thesis. And the idea was, we heard a lot of times, or like the literature often says that if you have a certain number of transistors added, you can detect it with this method. So the question was, okay, so if you can detect if 100 transistors have been added to your chip, how can you build a Trojan that doesn't add a single transistor? So it should not be able to detect. The question was, can we build Trojans without adding a single transistor? And we also had this, the attack scenario would be the manufacturing stage, and our Trojan should also be very easily be inserted during the manufacturing stage, which helps if you do it at the slowest level. And the idea actually turned out to be very simple, what I did. So this is like now a toy example. We later see that this toy example actually leads to a useful Trojan. So imagine you have an inverter, and you want to change the functionality of this inverter. In this case, you want to simply make the inverter always output 1. So always output VDD. So always give it a constant 1. But you want to do it in a way that it's pretty much impossible to detect optically. So if you look at if you make a picture of the transistor, of the inverter, it looks still like an inverter. But in reality, it always outputs a 1. And so if you look at an inverter as a PMOS and NMOS transistor, so we look at the PMOS transistor. This is how a PMOS transistor looks like. It's simply, it has a source and the drain region that is doped positively and sitting in a negatively doped N-well, and has this gate, and depending on what voltage the gate has, so if it's a 1 or 0, the output is 1 or 0. So it's, that's a simple transistor, and the question is, if we now simply if we make a connection between source and drain using metal, then we have a constant output of 1. But it would be detected easily because metal can be seen optically quite easy. So what we simply did is say, okay, let's also dope the source and the drain region negatively. What that actually physically means is that we have a constant connection between source and drain. So it's really simple. But we haven't changed the metal or the polysilicon. We have just changed the dopant polarity. And it turns out this change is very easy to do. We don't have to change the process of producing anything because there are some gates called N-wells that basically look like that, but they're not supposed to be transistors. So the bottom line is now we have a constant connection, and it's very hard to detect that optically. And if we look at our inverter, what we now have, we have a constant connection between VDD and the output. We still have like a second transistor down here. But basically, I will not go into detail, but you can use the same technique of dopant modification to basically remove this transistor so that at the end you have an inverter that always outputs a 1. And while I showed it with a simple inverter, you can do the same modification to pretty much any digital gate you want, including registers. So the remaining question is, can we build meaningful Trojans that pass functional testing? Because at the end, we want to make a modification that gains us something, right? We want to gain something, and like I mentioned, every chip will be tested. So if it doesn't pass normal testing, it's not useful for us as an attacker because it will not be used. I actually used 2 case studies. The by far most prominent one was a case study where I said, okay, let's take a design like Intel's Ivy Bridge random number generator, which produces very good secure random numbers. And it works as follows. The random numbers are actually generated by something called a weight matcher, which is a cryptographically secure pseudo-random number generator. And it has a 256-bit state, and that's kind of important for us. These 256-bit states will contain true random numbers. And they're seeded from something called a conditioner, and finally from the actual real true random number source, the entropy source. Now the important thing basically to remember here is that it's a very, very solid design. So the random numbers generated with this design are very, very good. They kind of have assurance that they have full bit entropy. And in addition, there is something called a built-in self-test that continuously tests that the entropy source is working correctly, and at every power-up, also the digital part. So the weight matcher and the conditionalized digital part, that it's working correctly at every power-up. So what do? We have inserted a dopant Trojan into this weight matcher, and to be more precisely, into this 256-bit state, where we basically have set some of the bits to a constant 1 or constant 0, to a secret constant that we as a designer of the Trojan know, but is unknown to everybody else, with the result that we, as the Trojan owner, can predict random numbers with a high probability. So instead of, like, if you have keys that are generated with that modified true random number generator, then we, as the owner, can predict keys, while for everybody else, it's impossible to predict keys. Now, the important part here is that it's nice that we now have, that we can predict keys. The question is it not detected during the built-in self-test? And for security reasons, it's actually often good to not give an attacker too much access to critical information, such as a true random number generator that generates keys. So it's actually, for security reason, we are using the built-in self-test to detect if something goes wrong. And how it works is you're basically doing this built-in self-test. You give a fixed input to the weight matcher, you generate bits, and then you compare it to a checksum. And like I mentioned, we have modified this state, right? So if you give the same fixed input, we will suddenly have different outputs. And these outputs will not match, so they should be detected, right? But what happens is that the checksum that is generated is identical. Why is that? Because we cleverly chose the constant in a way that it would not be detected, that it would match, despite the fact that the other bits don't match. And here's the thing, that these tests are really, really good at detecting random faults, because what we actually did was something called a stuck-at fault, something that is being tested against, built-in self-test test against this. But the thing is that such a stuck-at fault happens, and it doesn't get detected. It's so small that you can ignore this probability. But we don't do random modifications, right? We make targeted modification, so now it is possible again. So the output basically of this Trojan was that the keys that are generated with that would be insecure, because we as an attacker can use them. But they would be very hard to detect using this optical inspection, because detecting the dopant modifications is really, really difficult. And it still passes functional testing, as well as the numbers that are generated look like true random numbers. So if you apply the random number test on it, they will tell you, yeah, it's a true random number. There was actually also a second case study. I will not go into detail really what that is. Just wanted to mention, in the previous example, we basically modified the digital behavior of the circuit. In this example, we didn't modify the digital behavior, but only the power consumption. So we modified the power consumption in a clever way that it would leak out secret keys, which it shouldn't do. Testing again would pass. Why? Because we have not changed the logic function of this gate. So that just wanted to show that these type of attacks are quite versatile. Right? It's not restricted to one case. You have to be kind of creative to use it efficiently. So that was basically the technical part. So we come to the main takeaway. Basically, what we showed here is that we can build meaningful hardware Trojans without adding a single transistor. So from a technical perspective, you can build Trojans that are quite powerful and that are extremely small. How difficult it is highly depends on the system, and of course also on the attacker's capabilities. And it's really hard to tell, is it possible to insert a Trojan easily or hard? Because if you look at really the lowest level, it's hard to predict what happens at its lowest level. So I, for example, worked also on a project where we wanted to insert a Trojan at this lowest level. We found to took a couple of hours, I find a suitable position, and then somebody said, oh, I made a mistake. I changed this little bit part in the top design, but it shouldn't affect your part. It totally changed it, so it wasn't possible anymore what I wanted to do. So I needed to do something else. So it's really hard to figure out what's going on. And one thing on a personal note is, so this was published in 2013, and a year later, in 2014, there was actually a paper that showed how to detect these dopant changes optically. I like this example really because I know that when I published this in 2013, some people were not happy about it because I told the bad guys how to build hardware Trojans that cannot be detected. So I just want to show you the example that if we don't show people how to detect something, we'll never be able to defend it, because I was simply not knowledgeable enough about this whole testing community to come up with this method that the Japanese guys did 1 year later. So that comes to the point that it's basically cat and mouse game, and we really have to look at both sides to win it. And I think even proposing attacks that we don't know how to defend against today, in the long run, makes us much more secure. So to wrap it up, so is it hardware Trojan a threat to legacy weapon system? From a technical perspective, yes, you can build meaningful hardware Trojans. And there's also no clear guideline of how to detect it. So we don't have these 5-step, do that, and then you're fine, you don't have hardware Trojans. And one reason for that is that we don't really understand enough yet of how to build hardware Trojans. So I can maybe give you an example for my Trojan, but not for the Trojan that somebody else might do. So it's probably, my personal opinion is also it's very high risk. So if you build a hardware Trojan, it's much easier, I think, to track it compared to software attacks, because you cannot just simply hide behind an IP. If you are the manufacturer, you modify the chip, it's basically only you who could have done it. So to conclude, hardware Trojans are, in my opinion, an extremely high risk, high cost, and high gain attack, because it is very difficult to build a meaningful hardware Trojan into a system. If you get detected, it's quite likely that it can be tracked back to you. But on the other hand, if you do it very well, you can also gain a lot of it. So whether or not it's realistic, it's, well, it depends on the system, I guess. Okay, that's it. Thank you very much for your attention.
Okay. I know that you are tired. I don't know if you have also questions. No questions? So as I understood, this it's not science fiction. This can happen, yeah? So I'm coming from the development design. So I have this code bobbing in my brain, and I would like to know if there was a possibility, some kind of a material that you put in a design, in a chip, that it's golden and you can test it, but after a period of time, it just fade away. I mean, like 2 years after, these gates are fading away and it's producing another gates that nobody's retest. Could be this possible?
Actually, there has been work on that, basically on a time bomb. So they showed that they made some modification to the processing step, so that, as you know, computer chips can also fail, right? After some years, there's a high chance that they will fail. And they basically modified it in a way, or said, if you do it like this, then they will fail after a year or two. So if you actually test it, it will be fine. If you do accelerated aging to test it, up to a certain point, it will be fine. And then if it's in the field for 2-3 years, then it will fail. So yeah, that research direction is already has been proposed, and it's feasible technically.
Okay, I'm happy that I don't have this idea myself. Okay, so thank you again, George. Just, I don't know if you're married. There's this proverb Chinese that says if you want to be happy for a month, get married. But if you want to happy for your life, be a gardener. So, so follow this. I would like to remind you the app. So just give your feedback. There is also a Tallinn tour, yeah, in the afternoon, and also for the wild animals for the night. So be tomorrow 9 o'clock here. We have also interesting sessions. I hope you enjoyed. And thank you very much for your attention.
Good stuff.